Hey, physicists. We've been talking about light recently as part of our waves unit. I want to continue to talk about light. Specifically in this video, I want to talk about how light behaves when it enters different media and how we can make sense of that mathematically. The changes that we observe with the naked eye in light, how they can be reflected mathematically, and how we can be predictive based on what media light is traveling into. So the first thing to consider is the focus question: how can I determine what path light will take? Right, it's a different way of saying what I was saying, that we're interested in how it travels through media. This is part of Unit 5 on waves. And we're going to study what we call refraction, which is that change in light. Now, we perceive this as sort of a strange bending. If you've ever seen a light beam shined through different materials, like if we shine it into a water glass, the light is literally traveling from air into water. And because water is going to affect the light in a different way than air does, we're going to see the light sort of bend. All right. And this is perceived as the light enters here, and then we see it kind of coming down like that. Sorry, my hands are not on screen, like this, and then it almost like bends over and it's coming out like that. That's one way of seeing it. In other instances, we might see something like this picture, where it honestly seems to just kind of change direction. And then when it comes back out the other side and it's back in air, it's traveling in the same direction as before, albeit does not look like, it looks like it was shined at a higher height, initially, because we would have it coming out like this if it was going through straight forward. And that's because whatever type of material that glass is, it affects the light waves, okay? It changes the direction of the light. We're going to explore that. And the way that we make sense of this mathematically is through something called Snell's law, all right? And Snell's law, they're going to go over it in this lesson. And this video in particular, I'm not going to go through the lesson piece by piece. What we're going to do instead is we're going to answer some of the questions, but we're also going to try to handle the mathematical side, because I think this is the most challenging part of doing this work here. So I leave the conceptual part aside. We're going to focus on the math. We're going to focus on the Regents problems. So the diagram that you see over here, let me just grab my stylus. The diagram that you see over here, that is very similar to what you see in a Regents type question, where this dark red coming down from the top left into the center of the diagram line, that is the initial angle of the light, or what we call the incident angle. And then, or the angle that creates with a normal or an invisible line that is perpendicular to the surface change, that's the incident angle. And then we have the refracted angle, which is the normal in the second surface, the angle between the normal and the second surface, and the new path of the light. Okay, so light will change based on the medium. Its direction will appear to change based on the medium that it's traveling through. And so one thing that we need from our reference table in order to make sense of these directions is something that we call indices of refraction. All right, and we can find this, let me clear the screen. You can find this on the second page of the reference table. We see that air has an index of refraction of 1.00. I'm just going to circle that in blue. Sorry. That is right here. Okay, and then we can see all of these other materials have an index of refraction that is greater than 1. Okay, so air has the lowest index of refraction. As we do a problem or two, we'll be able to understand the implications of that. And so Snell's law is specifically this law, that if we take the index of refraction based on the material that light is traveling through, and we multiply that by the sine of the angle of incidence, again, that is the angle between a vertical normal that is perpendicular, or horizontal normal, it's just perpendicular to the border between surfaces. So the previous problem is perpendicular to the border between the surface, the air, and the glass that the light traveled into. We take the index of refraction for air, times the sine of the angle that the light makes between the normal and its ray. That should be equal to the index of the new material that light is traveling into times the sine of the angle of the refracted ray. And that angle again is made between a normal, between the surface, so invisible perpendicular line between the edge of the surface and the angle that the refracted ray makes with that normal. Okay, this will make a lot more sense once we take a look at a picture. Okay, now one thing that we'll answer beforehand, what happens to the value of sine of theta as theta increases from 0 to 90 degrees? So we just want to have a cursory understanding of how the sine of theta will change as the angle grows from nothing all the way to a right angle. And so we can take a look at Desmos here, and I see at nothing, it's 0. And then at 90 degrees, which I'm measuring in radians, so if you don't remember, pi radians is just another way to say 180 degrees. In other words, we have inches to measure length. We also have centimeters to measure length. Okay, those are just two different ways of measuring the length of something. Okay, and radians and degrees are two different ways of measuring the size of an angle. Okay, so when I say 90 degrees and I want to convert that into radians, that would be pi over 2 radians. Okay, so the second dot that I made is equivalent to not at 90 degrees. And we see that the sine of 90, because this is a graph of the sine, you can see over here that I'm graphing the sine. The sine of 90 degrees is equal to 1. The sine of 0 degrees is equal to 0. So I can see as I go from 0 to 90 degrees, the sine of the angle increases from 0 all the way to 1. And then it continues to oscillate. It goes back down to 0, down to -1, and then back up to 0 and up to +1. And it is a periodic function, so we see it making this kind of wave-like form. Now, I want to use this as a clearer example of what I was talking about with normals, incident and refracted rays, and different media, and the index of refraction. Okay, so we can calculate all the changes in the angle of the light, okay, that happen through here. So we have 3 different layers here. We start with just plain old air. We go into a perfectly rectangular layer of corn oil, and then under that is glycerol. And these are just 2 different materials that light can travel through and still be seen, okay? And so we don't need to stress too much about why we're passing the light through this. We just want to get a feeling for how light is changing and how we can track it. Okay, and so here's what I meant by in the normal, all right? We make the normal as perpendicular to the edge of the surface between the air and the corn oil. So I've got a right angle here, that's 90 degrees, and so that invisible or dotted line is my normal, okay? And I can see that they've already measured for me. We know that the angle made by the incident ray of light and the normal is 35 degrees, okay? So I can call my theta 1, I can call that 35 degrees. And then if I want to double check, my my index of refraction for air is 1.00. So if I go back to my problem, I can say that my N1, my N sub 1 is 1.00. All right. Now, what I need to find is this angle. So what I don't know, I'm going to write that in a different color. I'll choose red. What I don't know is this angle here. That would be theta 2. Because that's my new angle formed. All right, but I do know it's corn oil, and corn oil happens to be one of the materials tracked on my reference table. So I can see here that corn oil is 1.47. Sorry, that's 1.47. That's my index of refraction. So if I go back to my problem, I can say that N2 is 1.47. And these are all of my givens. I'm given this information. I always find it helpful to write down a list of my givens. and then I am trying to find theta 2, all right? And all I have to do is I have to plug my information into Snell's law and solve for the unknown, which I'm going to do down here. So just to repeat Snell's law, I know that n1 times the sine of theta 1, or the sine of my angle of incidence, is equal to n2 times sine of theta 2, or n2 times the sine of my angle of refraction. Okay, and theta 2 is what I don't know. What I'm going to do in this example is I'm going to plug in the actual numbers and then solve for theta 2. But you could also algebraically manipulate this, okay? So we have to do it in a couple steps. I'm just going to plug in this first step all the numbers that I have, all right? So I know I have that 1.00, and that's times the sine of 35 degrees. And that is equal to 1.47 times the sine of theta 2. Now my first step in solving for theta 2 has to be to divide both sides. Sorry, that's theta 2. Divide both sides by 1.47 to get the sine of theta 2 by itself. Now notice, I'm going to move this over to the other side of the diagram and keep going there. All right, but for now, before I do, what you'll notice when I rewrite it is that I'm not going to actually make a calculation yet. What I'm going to do is I'm going to make a final expression that we can plug into our calculator in one fell swoop, okay? So I have this over here. Now when I move it over here, I'm going to have 1.00 times the sine of 35 all over 1.47, and that's equal to the sine of theta 2. All right, and now here's the tricky part that I think a lot of students get messed up on. Actually, what I'm going to do is I'm going to make a little bit more space, and you'll see why. Equals sine of theta 2. Just make it like that. The reason I made that more space is that this is the tricky step people forget. I take this entire thing and I have to take the inverse sine of it, all right? And that is that sine to the -1 button on your graphing calculator, all right? So you need a graphing calculator for this, and I will show you how to use the Google calculator to do this. So I'm taking the inverse sine. What happens then is that the inverse sine and the sine cancel over here. And what I'm going to get on the right-hand side is just theta 2. And on the left-hand side, I will get a calculation for what this equals. So now let's pop this into a calculator. I have the inverse sine of 1.00 times the sine of 35 divided by 1.47. All right. So if you just Google calculator, Google will very helpfully pull up a calculator for you. We want to make sure it's in degree mode. Notice that degree is black and radians is grayed out. So I have it in the right mode. Okay, and thankfully my annotations shift over with me. So I have all this information. I don't have to remember it because I'm working on Zoom. Very, very handy. So other thing that you need to remember that I'm going to try to demonstrate here is that I need to write this from inside out. All right, so I can write inverse sine, and that's how you get to inverse. Notice I'll do it again. If you click inverse again, you get back to all these functions. If I click it, then I can get inverse sine, and I can get the inverse of logs, which are these exponential functions. All right, so I can click sine to the -1 or arc sine. And then inside of that, I'm going to type things. I'm going to use parentheses rather liberally. So I'm going to use another pair inside here. And I'm going to say 1.00 times the sine of 35. It's a little bit extra what I'm doing. I don't have to multiply by 1. And that's because I already know the result is just going to be equivalent to just taking the sine of 35 by itself. Now I divide it by 1.47, and I'm going to close my outer parentheses. So just take a look at it really quickly. I have 1.00 times sine of 35 in its own set of parentheses, and then I have divided by 1.47 in the outer set of parentheses, and all of that, the arcsine is being taken of all of that. And I click equals, and I get my answer. And so theta 2, let's take it to one decimal place. It's going to be equal to, write it in, I think, 22. Oh, it'll actually be 23.0. When I round it up, the 6 rounds the 9 up to 0, and so I change it to 23.0 degrees, okay? And so this is how you make this calculation. So I'm going to clear the screen. I'll leave it up for one more second, just go through my steps. We write down our givens, we write down our find, we set up Snell's law, and then we plug in all the information that we know. First, we divide one of both sides by n2, which is 1.47. And then after that, we take the arcsine of the entire expression inside. And notice I don't make a calculation until I have everything on one side and just the variable, the unknown that I'm solving for, in this case, theta 2 by itself, all right? And then I do the calculation, and that is to avoid errors from rounding from making earlier calculations. All right, so this is what we were doing in this. You have some other examples that are related to the change in angle and how that affects the sine of the angle, whether it grows larger or smaller. There are other questions also about how a change, a drop in the index of refraction is going to affect theta. All right, what I'm going to just hint at there is that since n1 is being multiplied by the sine of theta 1 and n2 is being multiplied by the sine of theta 2, you could say they both need to have a set product. So if we lower the index value, we have to go to greater sine, so the angle must be increasing, okay? Again, I'll say if n1 is less than n2, then the angle of incidence must be greater than the angle of refraction, because we need to be multiplying that smaller n1 by a larger sine of theta 1. Then we're multiplying the bigger n2 by a smaller sine of theta 2. Okay, so these are the trends we'd observe. Let's take a look at one more to close out. This is a light ray with a frequency of 5.09 times 10 to the 14 hertz, is traveling in water and has an angle of incidence of 35 degrees on a water-air interface. At the interface, part of the ray is reflected from the interface and part of the ray is refracted as it enters, okay? And so I just want to scroll down to the calculation. We have to calculate the angle of refraction of the light ray as it enters the air, okay? And so I'm just going to go back here so we have the information, all right? We know it's light. We know that it's traveling in water. So if we're going to go back here, I have to use my reference table, and I have to find the index of refraction for water. And here I've got it. It is 1.33, okay? So I'm going to clear that, go back to this. Okay, goes in, sorry, keep switching slides. So I know that my N1 is 1.33. And I remember from the previous problem that if I'm traveling into air, my N2 has to be 1.00. And now I also know my angle of incidence, all right? That's 35 degrees. So this time when I set up Snell's law, N1 sine of theta 1 equals N2 sine of theta 2. Then I can plug in what I know. Final thing that I know is theta 1 equals 35 degrees. I know that I have 1.33 sine 35 degrees is equal to 1.00 sine of theta 2. Now I'm going to make my life a little easier this time, and I'm going to simplify that to just equal sine of theta 2, because I know that 1.00 times it is going to give me the same number. All right, so I'll rewrite the left-hand side down here. So all I have to do is what I did before. I'm just going to write it once on the left-hand side, but I'm applying it to both sides. And that is that I'm taking the sign, the inverse sign of that expression, taking the inverse sign here too. Sorry about the small handwriting. And we move down here. And so I know that the sign, the inverse sign of 1.33 times the sine of 35 degrees, apologize for the handwriting, is equal to theta 2, because the arc sine and the sine are inverse operations. They cancel each other out. Once more to the calculator. Clear here. And again, I click inverse, I get the arc sine. And now inside of that, I'm going to write 1.33 times the sine of 35 and close my inner and outer parentheses. And that's going to mean that theta 2 is equal to 49.7 degrees when I round. So theta 2, sorry about that. Theta 2 is equal to 49.7 degrees. All right. So that will be our answer here. Okay. And then you could use the drawing tool to draw the angle of refraction. Okay. And that angle will be made with the normal. So we could assume, I'm not going to measure a 49.7 degree angle exactly. We know a 45 degree angle would be cutting this angle in half. Let's say just ever so slightly more than that. So we're looking at something that maybe is like that. Okay, when it refracts. But actually it's going to go this way. I apologize. So that would be 45 degrees that way. All right. And 49 would just be a little bit larger. So it's hard to see the difference, but it does bend a little bit as it goes that way. I apologize, I drew it the wrong way. That's what it would be. I'm going to clear this and draw it one more time. We know it's 49.7 degrees. So one more time, it's going to continue on its path, just bent, okay, meaning that this angle that it makes with the normal inside here, that is 49.7 degrees. Undo. 49.7 degrees represents this angle there. All right. And so we understand how to make calculations based on what media light is traveling through and what we know about it from before or after. Note, obviously, if we know both angles and we know one of the indices of refraction, we can calculate a new index of refraction based on that. Okay, and this is likely how scientists came up with the indices of refraction in the first place. We use air as sort of our base case of 1.00. And then depending on how the light refracts traveling through other media, we can calculate these indices of refraction. We can predict how light is going to behave as it passes through different media. So that is my support lesson. I hope this helps with problems having to do with indices of refraction, and I will see you next time.